Light fields are rapidly gaining popularity as they encode more visual cues than simple digital images in the forms of motion parallax and view-dependent effects, such as highlights. Several light field cameras and displays are becoming more and more available to consumers. Because of the enormous size of data, light fields are often captured using sparse set of cameras and transmitted using lossy compression methods that lead to the degradation of visual quality. Because of the hardware limitations, light field displays also introduce several artifacts when reproducing them. It is unclear how the distortions introduced on the way affect the perceived quality of light fields. In this work, we provide a publicly available dense light fields database along with human quality judgments obtained from a perceptual experiment for typical light field distortions. We also provide an evaluation, analysis, and extensions of existing quality metrics in the context of light fields and identify the challenges in light field quality assessment. Our database consists of scenes spanning large variety of different conditions, for example specular and transparent surfaces, thin and irregular structures, multiple light sources, multiple diffuse objects, high contrast color and texture, highly reflecting surfaces, shadows, fine structures, day and night, indoor and outdoor, glossy surfaces, complex surface appearance, and simple objects. For quality assessment, we consider typical light field distortions that are specific to transmission, reconstruction, and display. For each distortion, we generated multiple light fields by varying the distortion severity level. We considered well-known 3D extension of HEVC encoder for studying the transmission-related distortions with varying quantization steps. Cross-stroke model using a Gaussian and blur in angular domain is used to study the display-related distortions. For investigating the artifacts related to reconstruction, we chose several interpolation techniques that recovered dense light fields from sparse samples. We chose the distortions resulting from linear and nearest neighbor interpolation, as well as image warping using optical flow estimation. We also investigated the impact of using quantized depth maps. For different distortions were applied to every scene, resulting in 350 different light fields. For subjective quality assessment, we used a custom stereo setup using head tracking. Our setup allows the participants to view light fields in an unconstrained manner and judge the overall quality rather than individual views. Our setup also allows us to display high-quality reference light fields. Each stimuli is a pair of light fields taken from neighboring severity levels of the same distortion type. In each trial, the participants were shown a pair of light fields side by side, and the task was to indicate the light fields that a user would prefer to see on a three-dimensional display. Participants were given unlimited time to investigate the stimuli. 40 participants took part in the test, including both male and female ages 24 to 40 with normal or corrected to normal vision. The subjective results are scaled to just objectionable difference units that quantify the quality difference in relation to the perfect reference. For evaluation, we considered popular image quality metrics and extended their functionality to work with light fields. We also considered quality metrics for video, stereoscopic images, stereoscopic video, multi-view image and multi-view video. Here we show the quality of predicting subjective scores using different metrics. Our investigation indicates that when using densely sampled light fields as a reference, 2D image and video quality metrics perform well, although there is still room for improvements, as dense light fields may not be available in most of the practical applications. We also investigated the accuracy of the prediction when sparse light fields are used as a reference. The results show poor predictions in such cases. We also examined whether dense reference light fields can be approximated using optical flow information. Our experiments show that by doing so, the quality of prediction increases significantly, but it does not reach the accuracy of comparing directly to the dense reference. In summary, our work demonstrates that 2D image and video video quality metrics perform well when comparing distorted light fields to their dense versions. However, they cannot be used when the reference light field is not densely sampled. Such task requires new quality metrics. We believe that the perceptually scale data and light field dataset that we developed will facilitate the progress in this field. Thank you.